All right, let's dive right into this explainer. We're looking at a pretty fascinating question today. Why did some genuinely brilliant physicists feel the need to look beyond Albert Einstein's most famous framework? Now, obviously, we all know Einstein completely revolutionized our understanding of the universe. But the story of gravity doesn't just begin and end with him. There's actually a lot more to the puzzle. Because while general relativity is an incredible achievement, absolutely mind-blowing, it actually left a few massive plot holes, specifically regarding the true nature of inertia and some seriously weird cosmic numbers. And that's exactly what we're going to explore today. As beautifully constructed as Einstein's mathematical universe is, it had a few loose threads, and those threads bothered physicists for decades, ultimately leading to some truly mind-bending alternative theories. So here's our theoretical roadmap for this explainer. First, we'll look at what lies beyond general relativity, then we'll unpack Mach's principle, dive into Dirac's large numbers, and finally bring it all together with those alternative gravity theories. Number 1. Beyond general relativity. Let's quickly establish the massive unsolved problems that really set the stage for this whole cosmic mystery. You see, Einstein's theory gave us this stunning, elegant, geometric view of gravity. But brilliant minds pretty quickly realized it didn't fully explain where inertia comes from, nor did it explain why certain universal numbers align so perfectly. Think about it. When you're in a car that suddenly accelerates, that push you feel pinning you against your seat, that's inertia. But Einstein's equations couldn't completely pinpoint a definitive source for it. His framework actually allowed for the geometry of spacetime to have unconstrained elements, completely independent of the actual matter residing within it. And to a lot of physicists, that just felt like an unfinished puzzle. Which brings us to part 2, understanding Mach's principle. We have to talk about a 19th century philosopher whose ideas about inertia absolutely deeply influenced theoretical physics. The crucial point here is that, according to Mach's principle, the microscopic properties of a single spinning object are intrinsically tied to the macroscopic distribution of all matter everywhere in the universe. Ernst Mach suggested this famous thought experiment. If you spin a bucket of water, the water climbs up the sides. But why? Mach argued it's not just because the bucket is rotating, but because it's rotating relative to all the distant stars and galaxies out there. If the rest of the universe literally didn't exist, Mach believed the water would remain perfectly flat. Basically, your local inertia is completely dictated by the distant cosmos. Crazy, right? This quote right here brilliantly illustrates a kind of presentiment of a general theory of relativity, demanding that physical laws must reflect the whole universe. And Einstein himself was heavily inspired by this exact idea. He actually coined the term Mach's principle in the first place, and he tried desperately to embed it completely into general relativity. But as it turned out, general relativity in its purest form doesn't actually require the rest of the universe to exist for inertia to work. Because of that disconnect, incorporating Mach's principle directly into the field equations of general relativity became a major and highly complex objective in physics. A lot of scientists felt that because general relativity didn't fully satisfy Mach's vision, we absolutely needed an alternative, or at least a modified theory of gravity. Okay, moving to part 3, Dirac's large numbers. Let's shift gears entirely to the 1930s and look at another massive puzzle that totally challenged standard physics. Paul Dirac came up with the large number hypothesis. He proposed that a hidden thread connects the quantum mechanical origins of the universe directly to its massive cosmological parameters. He noticed something bizarre. When you combine certain constants from the microscopic atomic world with constants from the macroscopic cosmic world, you don't just get random noise. You get incredibly specific, massively large, dimensionless ratios that seemingly echo one another. And the number that kept popping up is mind-bogglingly massive, 10 to the power of 40. That's a 1 followed by 40 zeros. Dirac found this specific, giant number surfacing over and over again in completely different, seemingly unrelated areas of physics. For example, Dirac pointed out that if you compare the electrostatic force pushing a proton and electron together to the gravitational force pulling them together, that ratio is about 10 to the 40th. Okay, fair enough. But then, if you take the age of the entire universe and divide it by the microscopic atomic unit of time, you get the exact same staggering number, 10 to the 40th. Dirac just absolutely refused to believe this was a coincidence. So, to make the math actually work as the universe ages, Dirac concluded something radical. Gravity itself must be weakening over time. Now, this goes completely against standard general relativity. Because the age of the universe is obviously constantly increasing. If that ratio is going to stay equal to the physical forces, then the gravitational constant, the big G in physics, cannot be constant at all. It must be slowly decreasing as time goes on. And to make his equations balance out even further, Dirac proposed that new matter must be continuously created across the cosmos. Which brings us to our final section, number 4, alternative gravity theories. Let's see how all these philosophical and mathematical headaches paved the way for some truly brilliant alternative theories. In 1961, Carl H. Brans and Robert H. Dicke developed a leading competitor to Einstein's theory. And in their model, gravity depends directly on the distribution of matter in the universe. They basically took the static gravitational constant from general relativity and threw it right out the window. Heavily influenced by Mach's principle and Dirac's hypothesis, the Brans-Dicke theory introduces a whole new mathematical layer called a scalar field. This field essentially dictates the strength of gravity based on where all the matter in the universe actually is, dynamically shifting that gravitational constant over time. Around the same time, Fred Hoyle and Jayant Narlika proposed their own theory, inspired by the Wheeler-Feynman absorber theory. They essentially took Mach's idea to its absolute extreme limit. In their Machian conformal framework, the gravitational constant G is entirely determined by the mean density of matter in the universe. Meaning, if you somehow change the universe's overall density, you literally change how strong gravity is everywhere. And the implications of this are wild. While general relativity leads us to a standard Big Bang model, the Hoyle-Narlika theory argues for an eternal universe, a quasi-steady state. So as the universe expands, it doesn't just get emptier and emptier. Instead, little mini-bangs occur inside quasars, fueled by what they called C fields, or creation fields. These fields literally pop new matter into existence from empty space, just to keep the cosmic density perfectly balanced, and thereby keep the force of gravity balanced too. So, as we wrap up this explainer, I want to leave you with a rather provocative thought. Does the gravity keeping you in your chair right now depend on the distant stars at the very edge of the universe? Physics is an ongoing detective story, and the microscopic world might just be inextricably intertwined with the entire macroscopic cosmos. Whether general relativity remains the undisputed champion, or whether theories carrying the torch of Ernst Mach and Paul Dirac eventually crack the code, the idea that every atom in your body might be mathematically locked in a dance with the farthest edges of the universe is just staggering. Keep questioning the consensus, because in physics, the biggest mysteries almost always hide in plain sight.